Okay. Homework is almost done. I almost got it posted before class, but I didn't quite have a chance. So I'll get it up tonight. You'll have until October 30th, Sunday, October 30th. In the homework, you're going to use the Hall of Fame data and do a couple of classifiers. I'm also going to ask you to, let me say something about the homework. I don't have it posted, but I can preview it. It will be Hall of Fame data, and we will only use these 6 predictor variables: hits, home runs, RBIs, batting average, on-base percentage, and slugging percentage. So you don't need to know anything about baseball to do this. These are all just numeric variables. The bigger they are, the better the player, basically. I'm going to ask you to do LDA and QDA. So I haven't shown you code for doing QDA. I have shown you code for LDA. The code for QDA is exactly the same, except instead of LDA, the function named LDA, you use a function named QDA. But the syntax otherwise is exactly the same. As a reminder of what we're doing with LDA and QDA, we are saying that an observation X for each player, we have an observation vector xi and Hall of Fame membership class indicator yi. So for each of the players in that data set, we have those pairs. And again, X, in this case, we're going to consider it a 6-dimensional vector. A 6 by 1 column vector. Each player has those 6 numbers that we're going to use as inputs. What we're doing with LDA and QDA is assuming that the distribution of xi, given the value of yi, is multivariate normal with some mean vector. How do I want to say this? Mean vector, let's say it like J of yi. The notation's a little ugly, sorry, but you don't have to really, I'll tell you what I mean in a second. The mean vector, 6 by 1 vector, if you're in the Hall of Fame, is one particular mean. So let's suppose there's mu1 for in the Hall of Fame, and there's mu2 for not Hall of Fame. And then let's say that this J of yi equals 1 if yi equals yes, and 0 if yi equals no. So I'm just trying to indicate, you tell me the class that the data came from, we'll say it's multivariate normal with a mean specific to the class it came from, Hall of Fame or not. And we have, most generically, we could say there's a covariance matrix that also is specific to class. So if we have this multivariate normal assumption, or multivariate normal likelihood for the data, and if we have prior probabilities Let's call them pi 1 and pi 2. These are prior probabilities of Hall of Fame and not Hall of Fame, respectively. Prior probabilities are probabilities that we assign that are without regard for the input vectors. Overall, if you randomly pick a Major League Baseball player, what proportion of them are in the Hall of Fame? You could make that your prior probability for Hall of Fame. But you don't have to do that. You can choose anything you want as the prior probabilities. But once we have this, which essentially is a likelihood, this is a likelihood or something that gives us a likelihood, this probabilistic assumption about what the input vectors are distributed as, and prior probabilities, then we can use Bayes' theorem to combine prior with observed data to derive posterior probabilities. Let's call these H. And this is a function of class. So let's say H of yi given the data for individual I. And Bayes' theorem says this is equal to a likelihood for yi times prior let's say, let me change this real quick. Let's say H of Hall of Fame, the probability that player I is in the Hall of Fame, given their inputs, equals, using Bayes' theorem, the likelihood of observing these particular data given Hall of Fame let me just write it this way. Likelihood of Hall of Fame, prior of Hall of Fame, divided by likelihood of Hall of Fame, prior Hall of Fame, plus likelihood of not Hall of Fame. I'll just say not with a bar, times prior of not Hall of Fame. This is just a writing of Bayes' theorem, which allows us to go from a likelihood. We are saying x given y. You tell me the class, I know the distribution of the x's and priors, to switching the ordering of the conditioning to now a probability distribution of class membership given the data. I'm not going to ask you to do these calculations manually. LDA and QDA are doing them for you behind the scenes. But this is what it's doing. It's computing this posterior probability for each of the classes. So after doing LDA, we would have estimated posterior probability of Hall of Fame for each player, and 1 minus that, the estimated probability of not Hall of Fame. And then classification for individual I. What we can do is compute the posterior probability of Hall of Fame for individual I and the posterior probability of not Hall of Fame for individual I. So suppose we have these two numbers, and LDA and QDA will give us these two numbers in its output. Then one sensible thing to do would be to classify to which class has the biggest posterior probability. In a two-class problem, like this one, that's the same thing as just classifying to whichever of these two is bigger than 0.5. But in the homework, I've mentioned this in lectures once or twice. I'm going to ask you to dive into it in the homework. More generally, I guess, you could say, I will say y I hat equals yes. I'll predict Hall of Fame if the posterior probability of Hall of Fame is bigger than some arbitrary threshold. Call it kappa. Kappa has to be some number between 0 and 1. If you just call LDA in R, it's going to use kappa equal 0.5, the default choice. What I'm going to ask you to do in your homework is use cross-validation to look at different choices of that threshold. You will see that if you draw a picture with kappa between 0 and, say, 0.5, and CV-based accuracy, you will see that you can increase the accuracy with a choice below 0.5. So make a picture like this for both QDA and LDA. Make a picture like that. Tell me which kappa was the optimal kappa for LDA, which was optimal for QDA. And for that optimal model, so what is optimal choice of kappa for LDA and for QDA? And for that optimal choice, tell me some performance measures of the classifier. The simplest performance measure of a classifier, arguably, is the overall accuracy, the proportion of classifications that you make that are correct. But that's not the only way to hash the performance. You can ask about sensitivity, specificity, true positive value, positive predictive value, negative predictive value. I'm going to ask you for all of those, and I'll define them here. So I'm going to ask you, what are sensitivity, specificity, positive predictive value, and negative predictive value? And I want you to use cross-validation to estimate those. So what are these things? Let's consider what the outcome of our classification exercise would look like. We have some number of players who are in the Hall of Fame, and we have some number of players who are not in the Hall of Fame. And then we make predictions. We classify each player. So let me say this is truth up here, and this is prediction. Hall of Fame, not Hall of Fame. Another way to think of this is confusion matrix. A two-class case, it's just a 2x2 table, but what the ISL book calls a confusion matrix. Whenever we are in this cell or that cell, we did not make a mistake. But in this cell or that cell, we did. So what we could do is try to quantify this performance in different ways. Overall accuracy would just be add up the diagonals and divide by the total number of people. How many correct, or what proportion of your predictions were correct? That's an overall kind of global assessment of accuracy. That's not really sufficient for the Hall of Fame data, though, because the Hall of Fame data have so few people in the Hall of Fame that you can have very high accuracy by just saying no for every single player. So it's more informative to look at more specific assessments. So let me define some of these things. Sensitivity would be, how about we put numbers to these things? I'm going to call this first cell A11. Let's call this A12, A21, A22. So these are numbers, these are counts. There were 8 A11 people who were in the Hall of Fame that we correctly classified as being in the Hall of Fame. Sensitivity is the proportion of true positives, true Hall of Fame players, that we correctly classified as Hall of Fame. So this would be A11 over A11 plus A21. Sensitivity. Out of all the people who are actually in the Hall of Fame, what proportion of them did we correctly classify as being in the Hall of Fame? Specificity is similar, except that it's a calculation for those not in the Hall of Fame. Of all those who were not in the Hall of Fame, what proportion did we correctly classify as not in the Hall of Fame? So here we would have A22 divided by A12 plus A22. Two other things. Positive predictive value. You can Google these things. There's a Wikipedia page on them. Positive predictive value is the proportion of those we classified as Hall of Fame who are truly Hall of Fame. So what proportion of your Hall of Fame classifications are true? It's not the same thing as sensitivity. Sensitivity is what proportion of the true Hall of Fames did you get right? Now let's ask, what proportion of my claimed Hall of Fames, here's all the people that I claimed were Hall of Fame, what proportion of those were right? Then negative predictive value is this analogous thing for what proportion of our no's were correct. Here were all of our no's, A21 plus A22, and the ones we got right were A22. So, use cross-validation. Inside the loop, you're going to consider a variety of kappa estimates, or kappa choices. I give you the choices to use. I give you in the homework, consider this sequence of kappas. Inside cross-validation, you consider every single one of those, and you store sensitivity, specificity, PPV, NPV. Let me say something about LDA versus QDA. Back on the first slide here, I said that the assumption is multivariate normality. And initially, we've written this normal distribution as having a mean vector and a covariance matrix that's specific to class. Class-specific means and class-specific covariances. That is equivalent to QDA. That's what QDA does. What LDA does is restrict sigma 1 to be equal to sigma 2, to be some common sigma. LDA makes the assumption that each class is allowed its own mean vector, but they both have the same, or they all have the same covariance matrix. QDA is more flexible by allowing class-specific covariances. That means QDA is a more complex model, more flexible model than LDA. But that also means that QDA has more parameters to estimate, because you have to estimate 2 covariance matrices. Okay, so I'm going to post that as soon as I can right after class. There's going to be one, I think I'll put one question on there also to get you started on our next topic, which I'm going to start today, which is principal components, or PCA. Third slide. Yep. It's called positive predictive value. Is called negative predictive value. Positive predictive value. It's like, how much value do your positive predictions have? What proportion of your true positives, or your true, what proportion of your positive calls are true positives? There may be different lingo out there. If you can Google these ones, I know. There's a Wikipedia page on positive predictive value and negative predictive value. So in terms of characterizing a classifier, it's not really sufficient to just say the overall accuracy. It's much more informative if you can break it down by these things. The Hall of Fame data, we could have very high accuracy if we said no for everybody, in which case we would have 0 sensitivity. So the overall accuracy is great, but it's a worthless classifier because it has 0 sensitivity. All right. So let's start talking about our next topic, which is principal component analysis, or PCA. This is going to have a similar feel to linear discriminants. Remember that linear discriminants are linear combinations of the predictor variables that are chosen carefully. They're chosen so that they maximize the separation of the classes. It turned out that the answer to that choice of linear combinations was given by eigenvectors of a particular matrix. We're going to have the same kind of thing here with principal components, except we're not doing classification anymore. Principal components is a way of investigating what you could call structure in a multivariate data set. A multivariate data set composed of numerical variables. So let's suppose we have p numerical random variables. And suppose we want, okay, before I state the task, let me just say some basic things here. We have p-dimensional data. I have p random variables. Let's say that they have a covariance matrix, capital sigma, and a correlation matrix, boldface rho. Then consider any linear combination of those random variables. A1 transpose x, if x is a vector of p variables, then if we do some vector of constants, transpose x, it equals a1 x1 plus a2 x2 this linear combination of the x's. We're going to take multivariate data, n by p matrix of data, and we're going to be asking, can we take the p variables, this p-dimensional data, down to a smaller dimensional representation? That is, okay, can we do that task? Take from p variables down to a smaller number of variables. And the criterion for doing that is, let's go from p down to a smaller number in such a way that we preserve as much of the variation in the original data as possible. So we're going to be looking at the covariance matrix and or the correlation matrix, p by p in each case, and we want to ask, which linear combination of the p variables can we have that preserves as much of the total variability in this guy as possible? Okay, I'll leave it at that and fill in some blanks as we go. So linear combinations is what we're interested in. Let's consider a first linear combination, call it y1. This is a scalar. If we have p variables and we do a linear combination of them, we're left with a scalar. So here's y1, some linear combination of the x's. Here's another linear combination, y2, and another linear combination, yp. We know a couple of things about linear combinations of random variables from our earlier topics. Namely, the variance of yi, that's the variance of A transpose X, we've seen before that this equals A transpose times the variance of X, covariance of X, times A. We also have that the covariance between A1 transpose X and let's just say AI and AJ transpose X, any two linear combinations, is equal to AI transpose sigma AJ. These are things we know about linear combinations of random vectors. Okay, now what we're going to do is go in search of A1. Let's first go search for A1, where A1 is going to be picked such that it maximizes this. If you have n by p multivariate data and you want to scrunch it down to just one dimension, why would you want to do that? Well, if you can go from 10-dimensional data down to one-dimensional data, you can look at it much easier. Or two-dimensional data, you can make a scatter plot and look at it much easier. So let's try to go from p down to 1. If the task is to go from p down to 1 in such a way that we maintain as much of the information about what makes the individuals differ, if we can do it in such a way that we maximize the variability of the resulting linear combination, that's what we need to do. We want to maximize, we want to pick A1 such that this variance is maximized. So why does that make sense? If we're trying to, again, force p things down into just one dimension, we have zero information if, we lose all of our information if we take p variables down to something that's a constant. Suppose we took all p variables and boiled them down to a single number. There's no variance in that number. So there's no information about the players in our Hall of Fame data set in that resulting linear combination. An informative linear combination for, say, the Hall of Fame data would look like spreading out the players in some way, in some sensible way, from least prolific to most prolific, maybe. I'm trying to explain the data in one dimension. Explaining it will translate to more variation in the linear combination. So this, I probably didn't explain that real well, and it's a little bit counterintuitive maybe. Why do we want to have lots of variation? You know, we think about variation making it hard to do inference and things like that. But the idea here is we're trying to explain the differences between our individuals as much as possible. And if they're all packed in really close to each other, you can't tell them apart. There's no information about the differences in the players. An informative linear combination would spread them all out, ideally so that here's, you know, the low performers and here's the high performers, so that you can see the data in one dimension. So principal components is that task. It is find the linear combination that has maximum variance. And then go find the next best linear combination. But in the Hall of Fame data, suppose that the best linear combination is the average of these 6 variables. What if it's just 1/6 times hits plus 1/6 times home runs plus ... What if that one's the one that has the most variance out of all linear combinations? Then if I want a second linear combination, I could do 2/6 times hits plus 2/6 times home runs. That's not an average anymore, it's a weighted average. But that would have even more variation because it's just the first one times 2. And that would be worthless because it tells me nothing new relative to the first one. What we do in principal components then is we find the first linear combination based on it having maximum variability. Then we go look for another one that we try to maximize its variability subject to a constraint. And the constraint is that the first and the second linear combinations are uncorrelated, or in other words, orthogonal in a linear algebra kind of sense. So the first principal component is going to be the linear combination that best explains the data in one dimension. The second principal component is going to be the linear combination that best explains, but that is uncorrelated in a totally different direction from the first one. The idea behind that is that we're going to get these different angles or these different directions that explain the data. And we're forcing the algorithm to pick those directions so that they're all going in orthogonal directions. So we're not duplicating our learning. So here is the main result, really. The first principal component is the linear combination A1 transpose X that maximizes the variance of the resulting linear combination. For convenience purposes, we restrict the linear combinations to have length 1. So A1 transpose A1 is equal to 1. The computer does this for us. It picks the linear combination and it normalizes the coefficients to have length 1. Yes?
Do we still have to scale the data?
So the question was, do we have to scale the data? And we will talk about that. Long story short, if your variables are not on comparable scales, then you should standardize the data, or else we're going to get non-helpful things out of principal components. I'll show you examples of that. So if you have these 6 variables and one of them is on the scale of 1 to 10 and another one's on a scale of 1 to 1,000, you want to standardize the data first. What that translates to, I'll show you something in a second, but what that translates to is instead of working with a covariance matrix, unstandardized data have a covariance matrix, standardized data have a correlation matrix. Everybody has variance 1, so the diagonal is 1, and then the off diagonals are standardized covariances or correlations. And the answer to principal components is completely based on eigenvalue, eigenvector pairs of either sigma or, if we do standardization, rho. We have a slide on this in just a second. Right now we're saying we're not doing any standardization. We just have our data. The answer to this task, the first principal component, is defined as E1 transpose X, where E1 is the first eigenvector of sigma. The second principal component is E2 transpose X, where E2 is the second eigenvector of sigma. And then what we have is the variance of each of those principal components equal the corresponding eigenvalues. So principal components, in essence, is just doing eigenvalue, eigenvector decomposition of a covariance matrix or a correlation matrix. So let's look at an example before we get too far into the weeds here. I'm going to go to the Hall of Fame data. Okay, so let's go here, load the data in, and we're going to work with these 6 numerical variables. Here's the n by 6 matrix of unstandardized data. Here's the n by 6 matrix of standardized data. Let's go ahead and compute these things as well, the sample covariance and the sample correlation. Okay. All right, here is how you can do principal component analysis. There are actually 2 functions in R that do the same thing. There's prcomp and there's princomp. I'm going to use prcomp here. The way I can do it is prcomp, I give it my n by p matrix of numbers. I am here asking it to scale my data because here are the column means. So here are the variable means. Hits, the average is almost 1,200. Home runs, the average is 116. The others are in between. So that's a pretty substantial difference in scale. Home runs tend to be small relative to hits, and the others are in between. So I'm going to go ahead and standardize. Let's see what happens if we don't standardize first. prcomp. Let's print the object that's created, and let's print the summary of the object. If you just type the object name, hit enter, this is the output you get. So let's figure out what these things are. Before I try to figure it out, let me do something here. Eigenvalues and eigenvectors of S. Eigen S is eigen S. So slightly different. Let me try PrenComp. X scores. I'm going to try PrenComp. Data. Okay. By default, it's not going to standardize. Standardization would mean use the correlation matrix instead of the covariance matrix. Let's see what we get when we do this. I don't need the center and scale. Okay, so the output, let's use PrenComp. I like that one better. The output of PrenComp includes several things. The first thing I want to look at is what PrenComp calls its loadings. By loadings, what R means is the coefficients that define the linear combinations for the principal components. Principal component 1, the first linear combination that is most informative in terms of spreading out the Hall of Fame players. Not necessarily with respect to Hall of Fame status. This has nothing to do with Hall of Fame status. It's just looking at the 6 numeric variables. The most informative single linear combination is this one. 0.878 times hits plus 0.115 times home runs plus 0.461 times RBI plus what happened. So what R does by default, which I don't really care for, is it suppresses the values of numbers that it thinks are small enough to ignore. We can see all of them if I come down here and look at what are the eigenvectors of S. These are the exact same numbers as the, quote, loadings. So these last 3 numbers were deemed by R to be small enough to ignore. A lot of software programs do that because what we're going to do in order to learn from the principal component is, okay, this is the most informative linear combination. Remember when we did linear discriminants, we kind of said, what are the highest magnitude coefficients? And let's ignore the small coefficients, low magnitude coefficients, and roughly try to interpret what is the nature of that linear combination. So we might, if I were looking at these numbers, we might say, well, roughly speaking, the first principal component is a weighted average of hits with RBIs, with highest weight given to hits, and a little bit of contribution from home runs. But the biggest driver of spreading out the players in one dimension is hits and home runs. If you do that weighted average of hits and home runs to take your 6 numbers down to just 1, that will have the most variance, will spread the players out most of all possible linear combinations. Okay, the eigenvalues, this 548068, let me go ahead and compute the first principal component, show you what it looks like. the principal components. Let's come here. PCs. If I want to do that linear combination that is described by these coefficients, I can take my n by 6 matrix of numbers and matrix multiply it by that 6 by 1 vector of coefficients, like this. Let's do x matrix multiplied by the first eigenvector. Eigen S has two elements. There's an element named values, and there's an element named vectors. So if I say eigen S dollar vectors, first column, it's that first column of coefficients. So I can do the linear combination for all n people at once with this command. N by 6 times a 6 by 1 gives me back n by 1. This would be the first principal component. What I can also do is compute all of them at once. This is going to give me back an n by 6 matrix where each column is a principal component. Usually we don't want all 6 principal components. The point of doing PCA or any kind of ordination method like this is to reduce dimension. We're going to talk about in a second how we choose how many of them to include. But let's look at just the first one. Let's make, say, a histogram of the first principal component. It's like we've created a brand new variable. We had those original 6 ones, hits, home runs, RBIs, and so on. Now we have a brand new variable. It's a linear combination of those 6 ones. Here's what it looks like. And the claim is that that has spread out all the players the most of all possible linear combinations. The variance of this principal component is equal to the first eigenvalue. The most informative direction for explaining these data is given by the first eigenvector of S. And the informativeness of it is given by its variance, which is equal to its eigenvalue. If we tried any other linear combination of the variables, like let's try our linear combo, and let's do x times, let's just do a straight average. Repeat 1 over 6, 6 times. This is another linear combination of the variables, but we know for certain that its variance is going to be smaller than the one we just got. If you tried every other linear combination, as many as you wished, you would not be able to beat the amount of variability explained by the first one. Okay, that's the first principal component. The second principal component is uncorrelated with the first. That means if I do dot product of the first with the second, it's 0. Nope. Let's see. Not the PCs, the coefficients. Let's do transpose eigen S vectors 1 and the vector for the second one. Near as makes no difference, or just numerical rounding 0. And the variance of the second principal component is equal to the second eigenvalue of S. Something we saw way back in the beginning is that the sum of the eigenvalues of a covariance matrix equals the trace of the covariance matrix. The trace is the sum of the diagonal elements. So capital sigma, this capital sigma thing, P by P, the diagonal elements contain the variances of the P variables. If you added all of those variances up, in some sense, you're looking at the total variation in the data. And it turns out, like let's do the sum of the diagonal elements of S. It equals that. That is the same as the sum of the eigenvalues. So that means if we do eigenvalues divided by the sum of the eigenvalues, we have proportion of total variation that's explained by each principal component. In these particular data, without doing any standardization, the first principal component explains 95% of the total variation in the data. The second one, which has to be uncorrelated with the first one, and will therefore have smaller variance, only explains 4%. And then it drops down to nearly nothing. The reason that we have this, such a high proportion of variance explained, is because one of our variables has a high difference in scaling relative to the others. So in terms of explaining variation, we just need to primarily look at hits, because hits has such a big range. So let's change our strategy here. Damn it, out of time. Let's change our strategy to working with the standardized version of the data. I will do that next time. Okay, so I'm sure that was a whole lot of info, rapid fire style. We'll spend at least a week on principal components. We'll see it with several data sets. We'll get several opportunities to apply it and interpret it, make pictures of it, and learn from it. It's a really helpful tool. If I have data, first thing I do, or one of the first things I do is principal components. I do clustering analysis, and I do linear discriminant analysis if I have classes. Those are like bread and butter type of multivariate tools. Okay, homework's coming online tonight. No class Friday. I'll post a video either today or tomorrow.